Dear students, from our discussions in the previous classes, it is clear that the concept of stationarity is very important in the context of time series variables. We cannot use non-stationary time series for regression analysis, as we will get what is known as nonsensical, spurious regression. So it is absolutely necessary to establish the stationarity properties of the time series. Now the question is, how to determine whether a time series is stationary or not? Remember this, non-stationarity itself is divided into trend stationary and difference stationary. Trend stationary is not a serious issue because we can consider this possibility by introducing trend as an additional variable. But stochastic trends, difference stationary, is a potential issue. So we have to see whether the series is characterized by stochastic trends or whether the series is non-stationary. There are two approaches to determine whether a series is stationary or not. The first one is subjective method applied to time series graph and its correlogram. An examination of the correlogram of the time series. This is the old approach. The second one is formal statistical tests known as unit root tests. Unit root tests. So, for one method is correlogram. The other one is unit root test. So in this class we discuss correlogram. Today, correlogram is not actually used for determining whether a series is stationary or not. We have formal statistical tests known as unit root tests. But correlogram is useful for some other purposes also. When we model a time series into AR, MA, ARMA, etc., our modeling strategy is based on correlogram. So a knowledge of the correlogram is very important in the context of ARIMA modeling. That is a topic which we will discuss later. Now, the correlogram is a concept which we have introduced earlier. Correlogram is nothing but a plot of autocorrelation function against time, and rho k was defined as gamma k by gamma 0. That is, rho k is autocorrelation function. For lag k is gamma k by gamma 0. That is covariance at lag k divided by the variance of the series, which we have considered earlier. And while discussing this autocorrelation function, we have shown that rho k is less than or equal to plus 1, greater than or equal to minus 1. That is rho k, like any correlation, lie between minus 1 and plus 1. And if you plot rho k against k, say like this is k and this is rho k. A plot of rho k against k is known as correlogram. And while discussing different types of non-stationarity, we have shown that for a non-stationary process, the value of autocorrelation will be high even for many lags. For a stationary process, the value of autocorrelation declines quickly. For a white noise process, the value of autocorrelation is 0 for any lag greater than 0, like that. Now, we will get, if you plot rho k against k, you will get what is known as population correlogram. Population correlogram. But the problem is, to plot this population correlogram, the entire population must be known. But what we have is only a sample, a realization. So what we plot is sample correlogram. That is, we from a given realization, we calculate rho hat k, and this rho hat k is plotted against k. And when we plot rho hat k against k, we can define what is known as sample correlogram. And remember also this, autocorrelation function exists only for a stationary series. Because as we have discussed earlier, rho k is defined only for a stationary series. But sample autocorrelation function can be calculated whether the series is stationary or not. And it is given by rho hat k is equal to gamma hat k divided by gamma hat 0. Gamma hat k divided by gamma hat 0, where gamma hat k is equal to sigma of yt minus y bar into yt plus k minus y bar by a sample covariance, and divided by this gamma hat 0 is sigma yt minus y bar square by n. So we calculate sample autocorrelation function. And sample autocorrelation function exists whether a series is stationary or not. Whereas population autocorrelation function exists only for a stationary process. And remember this, if you plot rho hat k against k, you will get a sample correlogram. Now the question is, as we have discussed earlier, if the process is white noise, this autocorrelation function, when plotted against k, fluctuates around, actually it is 0 for white noise process. For a stationary process, it decreases quickly. Now the question is, if you have a time series, how many lags should be taken? Now, the lags are taken by considering 1/4 or 1/3 of the series. If you have 100 observations, take 25 as the lag length or 30 as the lag length, like that. Now, once autocorrelations are derived, rho hat 1, rho hat 2, rho hat 3, etc., we have to determine whether a particular value, say rho hat 1, or rho hat 2, or rho hat 10 is close enough to 0, so as to assume that this rho k is equal to 0. Once rho hat k is calculated from the realization, calculated rho hat k is used to make inferences about rho k. Suppose that we want to make inference about rho 1, that is between yt and yt minus 1, whether this autocorrelation is 0 or not. So we calculate rho hat k, and this rho hat k is used to test whether a particular rho k is equal to 0 or not. That is whether the covariance is, correlation is 0 or not. Sometimes we are interested in a group of autocovariances. Say we want to test whether rho 1 to rho 5 is simultaneously equal to 0. And remember this, if a process is purely random, then all the autocorrelations for lag greater than or equal to 1 will be equal to 0. Now, first we will explain how to determine whether a particular rho k is 0 or not. We explain how to determine whether a particular value of autocorrelation function rho k is equal to 0 or not equal to 0. Now, to explain this, we use a result shown by Bartlett. He showed that if a time series is purely random, that is, if it exhibits white noise, the sample autocorrelation coefficients for k greater than 0 are approximately distributed according to a normal distribution with the mean 0 and standard deviation 1 by and variance 1 by t. Bartlett has shown that if a time series is purely random, that is, if it exhibits white noise, the sample autocorrelation coefficients for k greater than 0 are approximately distributed according to a normal distribution with the mean 0 and variance 1 by t. That is, rho hat k is normal with the mean 0 and variance 1 by t. T is the sample size. As we are using time series, n is replaced by t. So, if a time series is purely random means if a time series is white noise. So, we are assuming that rho k, our null hypothesis is rho k is equal to 0. Tested against H1, rho k not equal to 0. So, if the null hypothesis is accepted, we will say that the process is stationary. That is, correlation between successive values of the variable is 0. H1 not equal to 0 means it is not stationary. Now, if rho k is equal to 0, rho hat k is normal with 0 and 1 minus t. Now, following the properties of standard normal distribution, we can write rho k as equal to rho hat k plus or minus 1.96 sigma by root t. Rho hat k plus or minus 1.96 1 by root t is 95% confidence interval for any rock. 95% confidence interval for any rock. And the decision rule is, if the hypothesized value is inside this confidence interval, do not reject H0. And what is the hypothesized value? Okay. That means if 0 is inside this interval, this is the interval, and if 0 is in the interval, do not reject H0. That means OK is equal to 0. That is, the process is stationary, otherwise reject it. Now, let me consider a simple example. Suppose that we have t is equal to 244 and 1 by t is equal to 1 by 244 is equal to 0.0041, and standard deviation is root of 0.0041 is equal to 0.0640. Now, 95% confidence interval, and suppose that for lag 10, O hat k is equal to 0.78. So, 95% confidence interval is O hat k plus or minus, that is 0.78 plus or minus 1.96, 1 by root t, that is 0.0640. That will give you 95% confidence interval as 0.7476 to 0.9984. This is the 95% confidence interval. And 0 is not included in this interval. So we reject H0, that OK is equal to 0. That means rho 10 is statistically different from 0. So this can be done for each. This can be done for each and every rho k. Now, an alternative procedure is, we can think about the 95% non-rejection region as 95% non-rejection region as plus or minus 1.96 into 1 by root t. 1 by root t. This can be used for all to test the hypothesis that a particular rho k is equal to 0. Now, if the value of rho hat is inside this region, inside this plus or minus 1.96 into 1 by root 10, then you do not reject H0. If the value is outside, you reject H0. And this is given in a slightly different way also. Suppose that H0, rho k is equal to 0 if absolute value of rho hat k is less than t alpha by 2 into 1 by root t, then it is stationary. Then HA rho k not equal to 0 if absolute value of hat k greater than t alpha by 2, then non-stationary. This is the procedure. Now, suppose that n is 36, 1 by root 36 is equal to 0.167, alpha is fixed at 5%, T alpha by 2 is 1.96, then T alpha by 2 into 1 by root 36 is 1.96 into 0.167 is equal to 0.327. This is the critical value. If, for example, for lag 5, the value of rho hat k is 0.599, H0 is rejected. The process is non-stationary. Any value greater than 0.327 will lead to rejection. Otherwise, there is no rejection. When rejected, the process is non-stationary. When not rejected, the process is stationary. Now, if you are using a software for calculating Correlogram, you will get the interval like this as dashed lines. Interval. This is the 95% confidence interval. And if that is minus plus or minus 1.96 1 by root t. This is what is given. If the value of an autocorrelation at lag 1, lag 2, lag 3, etc. lie inside this, the process is stationary. Or there is no significant correlation. Suppose that for lag 1 it is like this, etc. Then it is a sign of non-stationarity. So, in the computer, in the software, the 95% confidence interval is given as plus or minus 1.96 into 1 by root t. And you just see whether the calculated rho hats are within this region or outside. That is very easy in the Gretel software, EV software, etc. This is given. So the test procedure we have just outlined is testing for the significance of a single autocorrelation coefficient. Now suppose that you want to test the joint hypothesis that all rho k up to a certain lag, say up to 5, up to 10, is simultaneously equal to 0. To test such a hypothesis, we use what is known as the Q statistics, suggested by Box and Pierce. The statistics is Q is equal to N into sigma rho hat K square. K is equal to 1 to M, where N is the sample size, M is the lag length. Now Q follows chi-square with M. So if Q greater than Q critical, that is, if Q from the sample exceeds Q, critical Q value, that is critical chi-square value from the table for a chosen level of significance, reject H0. Reject H0. A variant of the Q statistics is Jung-Box statistics, known as LB statistics. And LB is written as N into N plus 2 sigma K is equal to 1 to M rho hat K square by N minus K follows chi square with M degree as well. Now, this LB statistics has better small sample properties than Q statistics. In the software EViews, Gretel, etc., Q statistics is reported. LB is another statistics. The purpose of both is to test the joint hypothesis that all autocorrelation coefficients up to a certain log is equal to 0. So this is the subjective method for detecting autocorrelation. If you want to test the significance of a single autocorrelation, we use Bartlett approach. If you want to test the joint significance of many autocorrelation coefficients, use Q statistics or Jung-Box statistics. These are test statistics used for testing joint hypothesis.